Hello everybody, this is lesson 4 of the lecture International Financial Markets. I will discuss slides 73 to 98 of chapter 1, How Capital Markets Work. In this lesson we will discuss various evaluation techniques that we need to evaluate financial market assets in chapter 2. As chapter 2 will show, very different kind of assets are traded on capital markets. Two technical procedures are important for the evaluation of these different assets: the discounted cash flow method and the internal rate of return method. Before we apply these procedures to the various types of assets in the next chapter, we will analyze them in some detail in the following. We will start with the discounted cash flow method. What do you prefer? A euro paid today or a euro paid to you in 1 year? Well, typically people prefer to have the euro paid today. If you ask them why, they usually answer that a euro paid today can be invested and will therefore be more worth than 1 euro in a year. And indeed, this is the reason why payments which take place at a certain point in time in the future are discounted by the interest rate offered for an investment over the same period. In this way, the present value of future payments is determined. In financial mathematics, this method is called the discounted cash flow method. The basic idea of the discounted cash flow method is we determine the present value of a flow of future payments either from an investment project or a financial market asset. Technically, these payments of different points in time are made comparable by evaluating each payment with a time-specific discount factor and adding up these comparable payments to the so-called present value of the total payment flow. The following numerical example show how this works. This table displays the yearly payments of an asset over the years 2008 to 2012. These payments are called the cash flow of this asset. The table makes the assumption that the appropriate discount rate over these years equals 5%. Consequently, every payment is discounted by the interest factor of 5%, which equals 1.05. It appears here in every year. And then this interest factor is taken to the power of the number of years when the corresponding payment is made in the future. For example, since the present value of this cash flow is calculated for the year 2008, the payment which takes place in the year 2009 is discounted by the interest factor 1.05 to the power of 1. And the payment which takes place, let's say, in the year 2012 is discounted by the interest factor to the power of 4. the resulting present values for the various years summed up to find the total present value of this cash flow is then 95.2 plus 90.7 plus 86.4 plus 82.3, and this results in the value 354.6. A comparison with the following table shows that a lower discount rate increases the present value. Here, a discount rate of 2% is chosen instead of a discount rate of 5%, so the discount factor is now 1.02. And of course, since the discount factor is smaller, the resulted present value is accordingly higher. 380.8 instead of 354.6. The problem of the discounting approach is that we have to find an appropriate discount rate, because as we've just seen, the discount rate has a very strong impact on the resulting present value. Theoretically, the appropriate discount rate should reflect the risk related to a payment flow. Uncertain payment flows, whose payment are based on estimated forecasts only, should be discounted with a higher discount rate than secure payment flows. Hence, the discount rate should include an appropriate risk premium. How can this be done? How to find the appropriate discount rate? In many cases, it is possible to find a market interest rate for a payment flow of the same risk class. If the payment flow is nearly certain, the market interest rate of a fixed rate security with the same risk structure, for example, a bond of a government with high creditworthiness, should be chosen as a discount rate. However, for many uncertain payment flows, it is difficult to find a market interest rate of exactly the same risk class. If the payment flow is uncertain and based on a forecast, for example, the dividend payments from a stock company, a market interest rate for exactly the same risk class is hard to find. In this case, concepts like the capital asset pricing model, CAPM called, can be employed to calculate an appropriate discount rate for such a stock. In Chapter 2, we will see how this works. Next, we will discuss the internal rate of return method. The basic idea of the internal rate of return method is, very often one knows the market price of an asset or investment project and its payment flow. In such cases, it is possible to determine the internal rate of return of the asset or investment project. Technically, this amounts to finding a discount rate that equals the present value of the payment flow with the market price of this payment flow. The following example shows how this works. The market price of this asset in period T is known. It equals 100 euro. The total payment this asset generates in period T plus 1 is also known. It equals 102 euro. Now, it is of course possible to set up the following equation. 100 euro equal to 102 euro over 1 plus the internal rate of return. This simple equation can of course easily be solved for the unknown internal rate of return, for which I've used here the shortcut I. This is the equation, and now we simply solve for the unknown variable I, and the result is of course 2%. Finding the internal rate of return gets, however, much more difficult if payments spread over more than just 1 year. If the payment flow consists of more than one period, for example 5 periods, calculating the internal rate of return implies solving a polynomial of degree 5. This involves the following problem. Formulas for analytical solution of polynomials exist only for polynomials lower degree 4. Hence we have no general formula that we can use to solve such a polynomial of degree 5. For example, in this table we have a payment flow over 5 years. We know the market price. What we do not know is the internal rate of return. Now we have no formula to solve this polynomial here for the unknown variable I. How do we find the unknown variable I? We must apply numerical solution methods. The English version of Excel offers, for example, the so-called IRR function, the internal rate of return function, for exactly this purpose. Please read the next digression for an explanation how this formula can be used in Excel to find the numerical solution. If you use Excel for this cash flow here and this market price, the internal rate of return equals here 3.78%. Consequently, calculating the internal rate of return typically implies the usage of a computer. If the internal rate of return of several payment flows or investment projects are calculated, it is in principle possible to select the payment flow with the highest internal rate of return as the most profitable asset. However, theoretically, one has also to take care of the risk implied by each payment flow generated by the alternative assets. Since an uncertain payment flow is riskier than a certain payment flow, the uncertain flow must offer a risk premium. One often used measure which takes care of both return and risk is called the Sharpe ratio, which was proposed by William Sharpe for these kind of problems. In this section we will see how the Sharpe ratio is calculated and used. The basic idea of the Sharpe ratio is to determine the risk premium paid per unit of risk. Therefore, the formula of the Sharpe ratio relates the risk premium from the internal rate of return of a specific investment to the standard deviation of the return of this specific investment. This is how the resulting formula for the Sharpe ratio looks like. We take the risk premium of an investment project and divide it over the risk involved in such an investment project. The formula is then the expected internal rate of return minus a measure for the riskless market interest rate, typically a bond, the return of a government bond with high credit worthiness. And then we divide this risk premium over the standard deviation of the internal rate of return. Standard deviation is the first root of the variance of the internal rate of return. So this formula is the Sharpe ratio. Of course, the higher the Sharpe ratio, the higher the risk premium per unit risk, and hence the more attractive is the investment. So we should select always the investment with the highest Sharpe ratio. Now let's make an exercise based on the Sharpe ratio. Which asset, asset A or asset B, offers the best relation between risk and return according to the Sharpe ratio? Let's assume that the risk-free return, the riskless return, is 2%. Let's switch to Excel to do these calculations. So what we need to determine is the standard deviation of the returns of asset A and asset B. The returns are given in this row here. We have only 3 states of the world to make the calculation simple: recession, normal situation, or boom. Now we have to calculate the standard deviation of these internal rates of return. The table helps us a bit to calculate first the variance and then the standard deviation, which is the first root of the variance. To calculate the variance, we need to know the mean return. So the mean return is the average value of these 3 internal rates of return that might realize. It's exactly 3%. Mean return is always the same. Now we have to calculate in the next row the mean deviation. The mean deviation is the return of every situation minus the mean return. Okay, and now we have to calculate the squared value of the mean deviation, which means the mean deviation to the power of 2. And now we have to calculate the variance. The variance is the mean of the mean deviation, so the average value of these 3 mean deviations. This plus this plus this over 3. The standard deviation is now the first root of the variance, so the variance to the power of 0.5. So this is the variance, 0.0408. And the Sharpe ratio is now the mean return minus the risk-free return. This is the risk premium which this investment project A provides, and then we divide this risk premium over the standard deviation to find the Sharpe ratio. So the Sharpe ratio of asset A is 0.245. Now we have to do the same calculations for asset B. With Excel that is simple. Since we have used formulas, we can simply copy the formulas on the corresponding place of the table, and then we clearly observe immediately that asset B has a lower Sharpe ratio as asset A. So, even so, the mean return of asset B is 3.33%, which is larger than the mean return of asset A, which is only 3%. The Sharpe ratio tells us in this case that we should prefer asset A, since the standard deviation and hence the risk of asset A is smaller, it's only 0.0408, than the standard deviation of asset B, which is 0.0573. Okay, this is our result. So according to the Sharpe ratio, in this case, you should prefer asset A and not asset B. You find the Excel table for this exercise below the video presentation of this lesson on Moodle. There's, however, a problem with the Sharpe ratio. The standard deviation of an investment, that means the measure for its risk, is typically not known. It has to be estimated based on forecasted future returns. In our above example, we simply assumed to know all these returns. For financial market assets, for example stock returns, such a forecast is typically highly inaccurate. Therefore, very often the standard deviation of a stock is estimated based on its past returns. Even though such a calculation is easily done and seems to be highly accurate and plausible, one has to be aware that the application of such a historic standard deviation for future investment decision implies the hidden assumption that the future will be similar to the past. For many kinds of stock, this assumption has proven to be wrong. So let's sum up. The discounted cash flow and the internal rate of return method are methods to calculate the profitability of different kinds of investments. The Sharpe ratio is a measure for the relation of risk and return of an investment. All these measures rely very often on a high degree of estimation and forecast. In the next chapter, we will apply these methods to the standard assets of the major capital market segments. So much for this lecture.